On March 23, 2025, a European space telescope built for an entirely different job pointed its camera at something it was never designed to look at, and in just 26 hours captured the largest, most detailed visible light photograph ever taken of the crowded, blazing heart of our own galaxy. Packed inside that single image are more than 60 million individual stars. And astonishingly, that's still less than 1% of all the stars that actually make up the Milky Way. It took the European Space Agency more than a year to fully process and release that image to the public, which finally happened on June 24, 2026. But this isn't just a beautiful photograph destined for a wallpaper or a museum wall. It's a working scientific tool, deliberately built to give astronomers a head start on hunting for planets we haven't even discovered yet. Planets that, in some cases, won't be detectable using this exact technique for years to come. The telescope responsible is called Euclid, and its entire mission is normally about something almost the opposite of this, mapping the invisible, distant scaffolding of dark matter and dark energy across billions of light years of the universe. For one single day, mission planners redirected it to look instead at our own cosmic backyard, and the results are already reshaping how astronomers plan to search for hidden worlds hiding in the most crowded, most difficult to observe region of the entire galaxy. By the end of this video, you'll understand exactly how this image was made, why it's so much more than just a pretty picture, and why the real payoff from this single day of observations might not fully arrive for years. This isn't a story about danger or an unresolved crisis, but almost it's something a little different. A genuine scientific achievement whose full payoff is still being deliberately set up piece by piece for a discovery that's only just getting started. To understand why this image is such a big deal, you first need to understand what Euclid is actually built for, and why looking at our own galaxy's center is such an unusual request for it. Euclid is a European Space Agency mission, launched in 2023 with contributions from NASA, designed with one overarching purpose: to help scientists understand dark matter and dark energy, the mysterious, invisible components that together are estimated to make up roughly 95% of everything in the universe. To do that, Euclid spends most of its time staring far beyond our own galaxy, mapping the shapes and positions of billions of distant galaxies stretched across enormous swaths of the night sky, looking for the subtle gravitational fingerprints that dark matter leaves behind. Euclid does this primarily through a technique called weak gravitational lensing, where the combined gravity of dark matter distributed throughout the universe on enormous scales subtly distorts the apparent shapes of distant background galaxies as their light travels toward Earth. By measuring those tiny distortions across billions of galaxies, spread across huge areas of sky, scientists can map out where invisible dark matter is concentrated and track how the universe's expansion, driven by dark energy, has changed over cosmic history. That's an inherently different kind of observation than photographing individual stars in our own galaxy. It requires capturing enormous numbers of faint, distant galaxies with extreme precision, rather than resolving crowded fields of bright, nearby stars. Pointing a telescope like this at our own galaxy's crowded central bulge is, in a very real sense, using the wrong tool for an entirely different job, except that Euclid happens to have exactly the right raw capabilities to pull it off spectacularly well. Its visible light camera, known as VIS, is sharp and sensitive enough to rival the Hubble Space Telescope's own wide-field camera in terms of pure image quality. But Euclid has one enormous advantage over Hubble for a task like this: sheer field of view. Each single pointing, one individual image Euclid captures in just a few hours, covers a patch of sky larger than the full moon, an area roughly 270 times bigger than what Hubble's main camera can capture in one shot. To manually stitch together an equivalent mosaic using a large ground-based observatory like the Keck telescope in Hawaii, astronomers estimate it would take around 2,000 hours of dedicated observing time. Euclid did the equivalent job in about 26 hours. That combination of sharpness and scale is exactly what makes the galaxy's central bulge such a uniquely difficult target in the first place. This region, the Milky Way's densely packed, extremely bright core, sits roughly 26,000 light-years from Earth, and it's so crowded with stars that most telescopes simply can't tell individual stars apart. Their light blurs together into an indistinct, overwhelming glow. Euclid's camera was specifically sensitive enough to resolve individual stars even in this incredibly crowded environment, without being blinded the way most other instruments would be. That rare ability is exactly why astronomers requested this one-day detour from Euclid's normal cosmological survey work in the first place. As Jason Rhodes, a senior research scientist at NASA's Jet Propulsion Laboratory who serves as both the U.S. Euclid Science Lead and a project scientist for NASA's upcoming Roman Space Telescope, put it, this was the only time Euclid has ever paused its normal sky survey. Redirecting a major space telescope away from its primary mission, even briefly, takes significant planning and justification. which meant this particular observation had to promise a genuinely high-impact scientific payoff to be worth the disruption. It's worth understanding a bit about NASA's Roman Space Telescope itself, since it's the mission this entire Euclid observation was designed to support. Named after Nancy Grace Roman, NASA's first chief astronomer and a key figure in getting the Hubble Space Telescope built in the first place, Roman is designed with a field of view roughly 100 times larger than Hubble's, while matching Hubble's image sharpness, giving it the ability to survey enormous areas of sky in far less time than previous space telescopes. One of Roman's flagship scientific goals is a dedicated years-long microlensing survey of the galactic bulge, specifically designed to detect thousands of new exoplanets, using exactly the same technique this Euclid observation was designed to support. Having Euclid's data already in hand before Roman even launches means astronomers won't be starting that survey from a blank slate. They'll have a detailed, precisely dated map of the entire target field ready to go from day one. Let's walk through exactly what Euclid actually produced during that single, carefully planned day of observations, because the numbers involved are genuinely staggering. Over the course of about 26 hours on March 23, 2025, Euclid captured a mosaic built from 9 separate pointings using its visible light camera. Each of those 9 images covered an area of sky larger than the full moon as seen from Earth. And stitched together, they formed a single mosaic roughly 18,000 by 18,000 pixels, about 324 megapixels in total, dramatically larger and more detailed than the output of even the most advanced consumer cameras. Inside that single mosaic, astronomers identified more than 60 million individual stars, along with nebulae, dense star clusters, and dark obscuring clouds of interstellar gas and dust that block the light of stars behind them. To put that 60 million star figure into proper context, even with that staggering number of individually resolved stars, astronomers estimate this still represents less than 1% of the total number of stars that make up the entire Milky Way galaxy, which is thought to contain somewhere between 100 and 400 billion stars overall. This single image, as enormous as it is really just a tiny, carefully chosen window into one especially crowded region of a galaxy, far too vast to photograph in its entirety from any single vantage point. The image itself was captured purely in black and white using Euclid's visible light camera specifically to keep the observation as stable and scientifically precise as possible. For the public release, the European Space Agency added color using supplementary ground-based data gathered from the Canada-France-Hawaii telescope, giving the final image its now recognizable golden star-studded appearance without compromising the underlying scientific data. The processing work behind turning raw telescope data into a publicly releasable image is itself a substantial undertaking, credited to image specialists J. Mtoukin, J.C. Kuyandra, and E. Burton at the CEA Paris-Saclay Research Center in France. Combining 9 separate pointings into a single seamless mosaic requires carefully aligning each individual image, correcting for subtle differences in brightness and calibration between exposures, and blending everything into one continuous, scientifically accurate picture, all while preserving the underlying data's usefulness for the actual research the observation was designed to support. That processing pipeline is part of why it took more than a year between when the observation itself was captured, in March 2025, and when the final publicly releasable image was unveiled in June 2026. That gap between capture and release is worth sitting with for a moment because it says something about how this kind of science actually works behind the scenes. The finished mosaic wasn't simply a matter of pointing a camera and downloading a picture. Every one of those 60 million stars needed to be cataloged, cross-checked, and calibrated before the data became genuinely useful to other researchers, let alone ready for public release. That year plus of careful, largely invisible work is a normal, expected part of turning a raw space telescope observation into a lasting scientific resource, even when the final result looks, to anyone watching, like it simply appeared overnight. Looking closely at the image reveals genuinely dramatic detail. Toward one side of the frame, thick, dark molecular clouds obscure entire sections of the galaxy's central bulge, blocking the light of countless stars behind them. Some of these dark, dusty regions are so opaque that astronomers refer to them as dark nebulae. Toward the other side of the image, at higher galactic latitudes, the golden glow of the galactic bulge becomes far clearer, with fewer interrupting foreground clouds, offering an unusually direct, unobstructed view deep into the crowded, stellar heart of our own galaxy. For additional context on scale, astronomers have compared this image against a wider field view from ESA's Gaia mission, a separate spacecraft that has spent years precisely mapping the positions and motions of roughly 2 billion stars across the entire Milky Way. Placed against Gaia's much broader, less detailed map of the whole galaxy, Euclid's new mosaic represents only a tiny, carefully chosen rectangle within that vast picture. But zooming into that rectangle reveals a level of individual stellar detail Gaia's wider survey simply isn't designed to capture. The two datasets complement each other well. Gaia provides the broad, galaxy-wide context, while Euclid provides an extraordinarily sharp, deep look into one specific, scientifically valuable patch of sky within it. This wasn't the first time astronomers had attempted to photograph this crowded region, either. Hubble had previously conducted its own survey of the galactic core, a project built from more than 350 individual images gathered over about 14 months, covering a smaller area than Euclid's mosaic, but at even higher resolution. Rather than competing with each other, the two datasets are designed to work together. Hubble's deeper, more detailed, but narrower view, and Euclid's broader, slightly shallower survey, both overlapping with the exact region NASA's Roman telescope will monitor, giving astronomers multiple independent reference points to draw on as they prepare for Roman's upcoming survey. That layered approach, a narrow, deep Hubble survey, a wide, fast Euclid mosaic, and eventually years of dedicated Roman observations, reflects a broader pattern in how modern astronomy increasingly operates. Rather than relying on a single telescope to answer every question about a region of sky, missions are increasingly designed to complement each other's strengths, with each instrument contributing exactly the kind of data it's uniquely suited to provide, while leaving the gaps for other telescopes built with different specialties to fill in. Hubble's exceptional resolution captures fine detail across a narrower field. Euclid's exceptional field of view captures breadth across a wider area in a fraction of the time. And Roman's eventual dedicated survey will add the one thing neither Hubble nor Euclid was ever designed to provide on its own: years of repeated observations of the exact same field, precisely what's needed to actually catch a microlensing event as it happens. Here's the part of the story that turns this from simply an impressive photograph into a genuinely important scientific tool. This particular region of sky was chosen specifically because it's one of the best places in the entire galaxy to hunt for exoplanets using a technique called gravitational microlensing. Microlensing works in a way that's genuinely different from most other planet hunting methods. Instead of watching a star dim slightly as a planet passes directly in front of it, or measuring a star's subtle wobble caused by an orbiting planet's gravity, microlensing relies on a chance alignment. When one star happens to pass almost directly in front of a more distant background star, from our point of view here on Earth, the closer star's gravity acts like a natural lens, bending and briefly magnifying the light of the star behind it. If that closer lensing star happens to have a planet orbiting it, the planet's own gravity adds a small distinctive additional flicker to that magnification, a brief, measurable signature that reveals the planet's presence and can even help determine its mass. As astronomer Jean-Philippe Beaulieu of the Institut d'Astrophysique de Paris explained, catching a microlensing event requires observing a candidate star continuously for more than 20 days, watching closely for exactly this kind of subtle unevenness in how its light gets bent as a foreground planet moves along its orbit. And critically, this technique only works well in extremely crowded fields of stars, which is exactly why the Milky Way's central bulge, despite being one of the hardest regions in the sky to observe clearly, is also one of the best regions to search using this specific method. Over the past 2 decades, ground-based telescopes using microlensing have already discovered close to 300 exoplanets this way, nearly all of them found by searching in the direction of our galaxy's crowded core. Unlike most other planet hunting techniques, microlensing is particularly good at finding planets in wider orbits than Earth's, including worlds that circle their star much farther out than Neptune orbits our Sun, and even rogue planets that have been ejected entirely from their original star systems and now drift alone through the galaxy. Euclid's new image already contains 51 known planetary systems within its frame, according to Beaulieu, and the data will help scientists study many more that are still waiting to be found. One particularly memorable example of what this technique has already achieved is a planet called Ogle 2005 BLG 3999LB, discovered through microlensing about 20 years ago by a team that included Beaulieu himself. That planet turned out to be a frigid, icy super-Earth, orbiting far enough from its star that Beaulieu has compared its likely surface conditions to Hoth, the fictional ice planet from Star Wars. Discoveries like that one illustrate exactly why microlensing is such a valuable complement to other planet hunting methods. It's uniquely capable of finding cold, distant worlds that would be essentially invisible to techniques that rely on detecting a planet's heat, its transit across a star's disk, or its gravitational tug on a nearby star. It's worth comparing microlensing briefly against the other major exoplanet hunting techniques to appreciate exactly what gap it fills. The transit method, responsible for the majority of confirmed exoplanets to date, works by watching a star's brightness dip slightly as a planet passes directly in front of it. But this only works for planets with orbits aligned almost perfectly edge-on from our point of view. And it's most sensitive to planets orbiting close to their star. The radial velocity method, one of the earliest techniques used to find exoplanets, detects a star's subtle back and forth wobble caused by an orbiting planet's gravity. But it becomes progressively harder to use for planets in wide, distant orbits, since their gravitational pull produces a slower, harder to measure wobble. Microlensing sidesteps both of these limitations, precisely because it doesn't depend on a planet's orbital alignment or its proximity to its star. It only requires the right chance alignment between a foreground and background star, making it uniquely capable of finding exactly the kinds of distant, cold worlds the other two methods tend to miss. Here's where the timing becomes especially significant. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in August 2026, will spend years conducting a dedicated microlensing survey of this exact same region of the galactic bulge, specifically designed to hunt for exactly these kinds of hard-to-find planets. Euclid's single day of observations happens to blanket the entire patch of sky that Roman will monitor repeatedly over the coming years, meaning Euclid has effectively provided astronomers with an early, detailed snapshot of every star in that field, taken before any of Roman's future microlensing detections even occur. That timing matters enormously for a subtle but important scientific reason. As the Euclid science team explained, once a foreground star and a background star drift apart again after a microlensing event, their separation on the sky gradually increases over time. Having Euclid's sharp, detailed image of the field from 2025, well before Roman's observations begin, gives scientists a genuine before picture. A fixed point of reference they can compare against Roman's future data to measure exactly how individual stars have moved and to determine, with far more precision than either telescope could achieve alone, the true mass of any planet Roman ends up detecting through microlensing. It's worth pausing to understand why astronomers consider this kind of cross-mission collaboration such a significant achievement in its own right, beyond just the exoplanet science it enables. As Rhodes put it, this project demonstrated that these two telescopes can work together to accomplish science that genuinely surpasses what either one was originally designed to do alone, establishing, in his words, a model for future coordinated observations that could unlock discoveries neither individual mission could achieve on its own. That's a meaningful statement coming from someone directly involved in both missions. Space telescopes are typically planned, funded, and operated as largely independent projects, each with its own specific scientific goals. Deliberately coordinating one mission's brief, unplanned detour to directly set up another mission's future flagship survey, years in advance, represents a genuinely unusual and forward-thinking piece of scientific planning. There's also a broader scientific payoff beyond planet hunting specifically. As astronomer Matthew Penny explained, one of the most exciting aspects of Euclid's observations is that they give scientists a genuine opportunity to test and refine existing models of the Milky Way's overall structure, comparing detailed, real observational data against theoretical predictions about how stars, gas, and dust are actually distributed throughout the galaxy's central bulge. Beyond exoplanets, this same dataset is expected to support research into entirely different topics as well, including the study of brown dwarfs, binary star systems, the motions of individual stars, and the distribution of dust throughout our galaxy, a genuinely broad range of scientific applications stemming from a single, carefully planned day of observations. Rhodes specifically pointed to two other kinds of objects. This combined dataset should help astronomers find more easily: isolated black holes and rogue planets. Isolated black holes, ones that aren't part of a binary system with a visible companion star, are notoriously difficult to detect directly since they don't emit any light of their own. Microlensing is actually one of the only techniques capable of revealing their presence at all through the way their gravity bends and magnifies the light of a background star passing behind them. Rogue planets, meanwhile, are worlds that have been gravitationally ejected from their original star systems and now drift through the galaxy without any host star to orbit. Both types of objects are essentially invisible to most other survey techniques, and both are expected to turn up in exactly this kind of crowded microlensing field once Roman's dedicated survey gets underway using Euclid's early data as a foundation. There's also a nicely poetic side to this discovery worth appreciating. Euclid's entire mission exists to study the parts of the universe we can't directly see: dark matter and dark energy, phenomena inferred only through their subtle gravitational effects on everything around them. For one single day, that same dark universe detective, as ESA has affectionately called it, turned its incredibly capable instrument toward the one place we can never fully photograph from any outside vantage point, our own galactic home, seen from within it. The result is simultaneously a practical scientific tool and, quite simply, one of the most striking portraits ever taken of the crowded, glittering neighborhood we all actually live in. It's also worth appreciating just how unusual it is for a major space telescope's operators to grant this kind of request at all. Every hour of observing time on a mission like Euclid is carefully allocated years in advance, weighed against dozens of competing scientific priorities tied directly to its primary cosmological mission. Diverting the telescope, even briefly, means displacing observations that were originally planned for that time slot, and doing so requires convincing mission scientists that the scientific return justifies the disruption. The fact that this request was approved, and that the resulting image has already generated this much scientific interest and cross-mission planning, is itself a signal of how highly astronomers ultimately valued the opportunity once it was proposed. So here's where this genuinely stands right now. Euclid's single day of observations, back in March 2025, has already produced the largest, most detailed visible light image ever taken of the Milky Way's core. More than 60 million stars, captured in about 26 hours, publicly released in June 2026. But the real scientific payoff from this specific image is still, quite deliberately, mostly ahead of us. NASA's Roman Space Telescope, launching in August 2026, will spend years conducting the actual microlensing survey this Euclid image was specifically designed to support, meaning most of the exoplanets this data will eventually help confirm, measure, and characterize haven't even been detected yet. That's what makes this story genuinely different from a typical, here's an amazing photo piece. This image is, quite literally, a time capsule, a precisely dated snapshot of tens of millions of stars, taken specifically so that when Roman eventually detects a new planet through a fleeting microlensing flicker sometime in the years ahead, astronomers will already have this exact before picture in hand, letting them measure that planet's mass and confirm its existence with a level of precision that wouldn't be possible from either telescope's data alone. The real question isn't whether our galaxy still holds worlds we haven't found. It clearly does. 51 known planetary systems already sit inside the single image, with countless others almost certainly waiting to be discovered in the same crowded field once Roman begins its dedicated hunt. The real question is how many of those future discoveries this one carefully timed day of Euclid observations will end up helping to confirm. It's also worth remembering just how much groundwork already had to happen before this single image could even exist. Years of mission planning, coordination between two separate space agencies, a competitive case made for briefly repurposing a billion-dollar cosmology mission, and more than a year of careful image processing, all had to come together before the public ever saw a single pixel of this mosaic. That's easy to forget when looking at a beautiful, finished photograph, but it's exactly the kind of patient, deliberate scientific groundwork that tends to produce the discoveries with the longest-lasting impact, rather than the flashiest overnight headlines. If you want to be here when Roman launches, and when the first new planets confirmed using this exact Euclid reference data start getting announced, subscribe to the channel and turn on notifications. Because when those discoveries come in, we'll break them down here with the real data, not the invented version. One day of observations, 60 million stars. A telescope pointed at the future, disguised as a photograph of the past. Whatever Roman eventually finds in this exact patch of sky, it will always be measured against this one carefully timed day in March 2025. A reminder that some of the most valuable scientific tools aren't built for a single moment, but for setting up a discovery that only pays off years down the line. That's a very different kind of achievement than a single dramatic breakthrough. It's patient, deliberate science, banking a payoff years in advance, and it's exactly the kind of long-term thinking that tends to produce the discoveries people are still talking about a decade later. Thanks for watching.